Alright, so this is our second video from Chapter 5 for Math 1560, Calculus 1 at U of L for fall 2017. We're still in section 5.1 here. We're looking at antiderivatives. Now we're going to look at what are called initial value problems. So these are problems where we want to find an antiderivative, but we want to find a particular antiderivative. So we saw in the last video that in general, when you find an antiderivative, it's only given to you up to some constant, right? The constant of integration. So we saw that, for example, if f of x equals, let's say, cos x, then a possible antiderivative, it would be f of x equals sine x, but I'd be off by some constant of integration. There might be some plus c that I have to account for there, right? And I don't necessarily know what c I want, and if I'm looking for sort of the most general answer, I would just leave that c undetermined. But there are times when this constant matters, right? Think about something like velocity. If you know velocity is a function of time, can you determine the position? Well, not exactly, right? Because v of t is the derivative of my position. Let's say x is my position, x of t is my position as a function of time. V of t is x prime, right? So if I can determine the antiderivative for v, well, that gives me, let's use this indefinite integral notation, right? I could write something like this. Well, the position as a function of time would be the integral of v with respect to t. But I really only have that up to some constant. I don't know what the constant is. And so what does this constant tell us? Well, this constant c, it depends on the initial position, right? If I have two objects that begin at different places but follow the same velocity pattern, they have the same velocity over some period of time, if they begin at different places, they're going to end at different places, right? Where they end also depends on where they begin, so we need this extra piece of information. What was your starting value, right? So we need the antiderivative, the general antiderivative, and then the starting value, and then we can actually get an exact antiderivative that fits all of these conditions. Okay, so here's a basic example. We've got a function f of x equals 4x to the fifth minus sine x, and we want to find, among all possible antiderivatives, we want to find the one satisfying this initial condition that when x equals 0, my function should have a value of 3. Okay, so as a starting point, we do this. We say, okay, so let's use this integral notation. So we do the integral of 4x to the 5 minus sine x dx. You don't have to use this notation, but it sometimes comes in handy. And since we have some difference constant rules for derivatives, those also work for antiderivatives. I can split this up, right? 4 times the antiderivative for x to the fifth minus the antiderivative for sine. And now I can say, okay, what's the antiderivative for x to the fifth? We add 1 to the exponent. We divide by the new exponent, x to the 6 over 6. Antiderivative for sine is minus cos. Minus cos gives me cos x plus c, some constant that I don't know. But now I can figure out that constant because f of 0 is going to be, so 4 over 6 is 2/3, 0 to the 6 plus cos of 0 plus c. So that is 1, cos of 0 is 1, plus c, and I want that to equal 3. Okay, well, there's only one value of c that's going to work there. It's got to be c equals 2. So the function that does the job for me here is going to be 2/3 x to the 6 plus cos x plus 2. And you can check that indeed f of 0 is equal to 3, and that if I calculate the derivative, I get back 4x to the fifth minus sine x. So it satisfies everything that I needed to satisfy. Alright, let's try one more. Now, in this example, I'm giving you the second derivative, and this is, again, if you're thinking of problems coming from, let's say, physics or somewhere like that, this is quite a common problem because if think of Newton's laws, right? Think of F equals ma, right? If I know the force and I know the mass, I can get the acceleration, but the acceleration is given by the second derivative of position, right? So there are a lot of physical problems where I'm able to figure out what the acceleration is, and now I want to figure out what the position is. Well, now I'm going to need a fair amount of information. I'm going to need more than just initial position. I'm going to need initial position and initial velocity. Let's show you how this works. So f double prime is 6x cubed plus 2x minus 3. So to calculate f prime, I reverse the derivatives once, right? So I go 6. The antiderivative for x cubed is x to the 4 over 4. 2, the antiderivative for x squared, x to the 2 over 2. The 3 is a constant. I can think of that as 3 times 1. We know that 1 is the derivative of x. So we get 3x plus some constant c. Okay, so let's clean that up. This is 3 over 2x to the 4 plus x squared minus 3x plus c. Okay. Oh, but now I know that f prime of 0 is equal to minus 2. F prime of 0, well, all of those x terms just go away, is equal to c equals minus 2. That tells me that f prime must be 3 over 2x to the 4 plus x squared minus 3x minus 2. Alright, so now I've got f prime. I can do the antiderivative one more time, and that's going to give me back f of x. So what's f of x? 3 over 2. I do the antiderivative for x to the 4, so I add 1. That gives me 5. Divide by 5. And then for x squared, it's 1 over 3x cubed. And then 3 over 2x squared minus 2x plus another constant. And, well, I shouldn't call this constant c as well, because it might be different from the one that we had above. Let's call this one c1. Okay, and f of 0, well, f of 0, of course, again, all these x's go away, is equal to c1. And I want f of 0 to equal 3. Alright. Now I've got my f of x. F of x is going to be 3 over 10 x to the 5 plus 1 over 3x cubed minus 3 over 2x squared minus 2x plus 3, right? So I can do the antiderivative twice, and as long as I have two pieces of information, the initial conditions for both f and f prime, I can recover my function. Okay. A similar, a variation on this problem in the language of differential equations, you would call this a boundary value problem rather than an initial value problem. This is one where instead of being given initial conditions for both f and f prime, I'm given the value of f at two different points. So how does this work? Well, it works the same way as above, except that when I calculate f prime, right, so I do my antiderivative and I get 3 over 2x to the 4 x squared minus 3x plus c, and I don't know what that c is, so I'm going to leave that and just call that c1. Right? I don't have any information yet that could let me recover c1. So I do the antiderivative again, and I get my 3 over 10 x to the 5 plus 1/3 x cubed minus 3 halves x squared. And now for c1, all I can do here is say c1x, and then I get another constant, say c2. right? So this time I end up with two different constants, a C1 and a C2. But I still have two pieces of information. F of 0 is going to be, well, again, all the x terms go away. I get C2. And f of 0 was supposed to be equal to 3. So that tells me that C2 equals 3. F of 1 is, so I put in x equals 1. I get 3 over 10 plus 1 over 3 minus 3 over 2 plus C1 times 1. I don't know what C1 is. C2, I know that C2 is equal to 3 now, and I want that to be equal to minus 2. Okay, so what's C1? Well, it's going to be minus 2 minus 3 minus 3 over 10 minus 1 over 3 plus 3 over 2. Bring all those constants over to the other side. And I guess if I wanted to, I could work out what this is, right? Let's leave it at that. I would have to get, what would I do? Common denominator would be 30, so I'd have to go through, get everything over my common denominator, clean it all up. I could write that as a single fraction, but that's probably not a good use of our time. Let's leave it at that. But again, note that I can get that constant, right? As long as I've got those two pieces of information, I get both constants, and I'm able to do something with them. I'm able to recover a function, right? So once I plug those values in, again, I've got my function, and there are no undetermined constants left. All right. So that's it for antiderivatives. We're going to leave this for a little while, and we're going to move on, and we're going to start talking about area. We're going to talk about integration, and once we've done the fundamental theorem of calculus, we'll bring antiderivatives back into the picture, and we'll see how everything fits together.